Okay, so materials is actually, compared to some of the other areas, relatively short. So let me sort of summarize the main points, and then I can answer any questions that you have. So at A-level, what we're mainly involved with is considering what happens when we apply a force to a material, usually to extend it. And usually we're looking at either springs or wires. Okay, so typically questions will involve springs or wires of a particular dimension, right? Length and cross-sectional area. Many of the ideas also apply when you compress materials as well, but we don't tend to worry about that at A-level. There's a little bit on density though. So for the sake of completeness, let me write the definition for density. Mass divided by volume. And this is useful, of course, because it allows us to compare the properties of materials, different substances, irrespective of their size, the size of the sample you're dealing with, density being mass per unit volume, measured in kilograms per meter cubed. Now that's relatively straightforward. You should be familiar with perhaps methods of measuring density. So one way is to measure the dimensions of a sample or of an object, measure dimensions, and then obviously weigh this sample, measure the mass, and then use the equation. The alternative, which is useful for irregular objects, is to use the displacement method of finding the volume, so that you find, what you do is you submerge fully the sample you're interested in a liquid of known density, usually water, although actually it doesn't matter because what you're interested in is the volume displaced. So fully submerge, it's important that it's fully submerged in water and measure the volume difference. Volume change. And so you need to use a measuring cylinder typically. Fully submerged in water, measuring cylinder. So that's just the first little statement on density, definition and how you might measure the density of an object. Let's get straight into then what happens when we apply a force to a material. And I'm going to draw a spring just because it's easier to draw initially at least. And we're going to hang a mass or masses off the spring so that it extends by a certain amount. So imagine we've got a spring, it has a certain original length, L, and then it extends by a smaller distance, delta L. And of course, the force we're applying is usually labeled F. From GCSE, probably, you are familiar with the idea that the force and extension, let me draw those straight. The force and extension behave like this. You get direct proportional or direct proportion up to a certain extension, and then you get nonlinear behavior, and then depending on the material you've got, you can get more complicated behavior after that. So the line can do something, as you can see on the right, the blue line here does something more interesting, but let's just look at the first bit. So initially we get straight line through the origin. So this indicates that force is directly proportional to the extension. And we know that this equation here, where we introduce a constant, allows us, if I can spell, it's not the spring constant, that allows us to, for a particular spring or a particular sample, work out the extension for a given force or vice versa. You should at this stage be really comfortable with direct proportionality. So I'm going to not say much more about that for now. At this point, which I'm going to call the limit of proportionality, we get divergence from this Hookean behavior, and we get a curve up to this point, which I'm going to call the elastic limit. And then, of course, the line does continue after that. So what's important is that the limit of proportionality is the point beyond which Hooke's law is no longer obeyed, because we're no longer a straight line through the origin, right? It's started to curve. The elastic limit is the point beyond which plastic deformation occurs. And beyond which plastic deformation occurs and the sample is permanently deformed. So the difference between elastic and plastic is that elastic behavior is behavior where you deform a material and it returns to its original shape or original length. So an elastic band is kind of a good example, because if I stretch an elastic band and release it, it goes back to its original state. Similarly, if I pull a mass and a spring down without going beyond the elastic limit, when I let it go, it'll return to its original length. So that's elastic behavior. Material will return to its original shape, length, state. Plastic behavior is behavior where the material will not return to its original state. A good example would be blue tack. Okay, let me get some blue tack. Because I just have some lying around, of course. Here's some blue tack. If I deform blue tack, it doesn't return to its original state, does it? It remains deformed. So this blue tack is behaving plastically because when I deform it and extend it, it is permanently deformed. Okay, it doesn't return to its original state. So that's the difference between elastic and plastic. Interestingly, you can go past the limit of proportionality and retain elastic behavior. So even if we go past the limit of proportionality, you see in this yellow bit here, we can return to the original length or original shape, but only up until the elastic limit.
So
yes.
Then what's the point of the limit of proportionality if it returns back to its start?
Because that's where Hooke's law is no longer obeyed. That's where we can no longer say the extension is directly proportional to the force.
Oh, so during that yellow part, it's not directly proportional, but it's close, like it's closely directly proportional. Sorry.
Well, it's not directly proportional, but it's still behaving elastically.
Oh, okay.
So it will return to its original state.
Oh, okay.
Right. While Okay, to the right, you can see I've got this graph which has 3 different lines on it. Now, for now, I want to ignore, just let's not talk about material C just for a minute. We'll get there. Let's look at the black line and the blue line. Material A, maybe you can chip in, one of you. What does the steepness of that line tell us? How, if you were going to compare material A to material B, based on the steepness of that Hookean region, what would you say?
A is, wait, is stiff the right word? Or
Yeah.
is it brittle?
So it's both, in fact, right? So material A is stiffer than material B because it requires more force to produce the same extension, right? So material B, you only need this amount of force, F, blue F, whereas to get the same extension, we need a larger force for material A. So it's definitely stiffer, and it is actually brittle as well because we can identify this point, or I could have labeled it as the breaking point or fracture point, and that would be the point at which material A breaks, okay, or snaps. So the fact that it does that very soon after the elastic limit means that it's brittle. So imagine something like glass, or well, glass is a good example as any. Okay, some plastics would be quite brittle as well, but you can deform them. They're quite hard to deform, but once you deform them a certain amount, they break very suddenly. Whereas, how might you describe material B rather than brittle? Good. So material B would be more what you describe as ductile, in that it can be deformed plastically for quite a long extension. Okay, so there are 2 types of material that category that you should be able to distinguish between. Okay, brittle, not much plastic deformation, sudden fracture, ductile material, lots of, a considerable amount of plastic deformation beyond the elastic limit. Good. Oh, before I move on to material C, the area underneath, let me go back to my graph here. If I were to ask, what does the area underneath represent? What would you say?
Work done.
Good. So it's a forced it's basically a forced distance graph. And the area underneath is, the work done on the material, or the energy stored. And that's equal to half F times delta L. And if we're obeying Hooke's law, which we usually are, certainly in the straight line region, we can actually write half K delta L times delta L, which gives you the energy stored being half K delta L squared. So both of those are actually quite useful to be familiar with. Half delta F delta L and half K delta L squared.
Why is there 2 delta L's?
Oh, because I've written here for F here, I've written in, using Hooke's law, K delta L.
Oh, okay.
So then you get a delta L squared.
Okay.
Okay. Let's look at material C. Why not? What can you tell me? What do you think material C might be?
Blue tack?
Possibly.
Plastic.
Yeah, it could be plastic. What does it not obey?
Hooke's law.
Yeah, it's not showing any straight line section, It doesn't obey Hooke's law. It's probably something like rubber. Like rubber is the classic example of this kind of behavior, but plastic would be good as well. Yeah, sorry, I'm just checking something. Yeah, so the reason for this usually is to do with the form of this curve is to do with the makeup, the molecular makeup or structure of the material. So rubber typically doesn't obey Hooke's law, fine, or plastic. Have you ever heard of hysteresis? Anyone? Hysteresis. Let me write that down.
Nope.
So, hysteresis, this is something that it's not actually mentioned on the syllabus, but I'm going to just mention it anyway, is a property of a material or substance where when you extend it, it behaves in one way. So this is when you're extending it. When you de-extend it or remove the force or remove the load, it behaves slightly differently. So deloading. So hysteresis is that property where you get a different behavior on extension and on de-extension or deloading. It's worth being aware of. So rubber, this is more classic rubber behavior, hysteresis. So it's probably, I mean, rubber, that could be rubber, material C, but it certainly is, does not obey Hooke's law. So yeah, it could be like it could be plastic, rubber, or as you say, I mean, blue tack to some extent actually would fit the bill. So what could you say? Resin or some kind of gum might behave like material C. Right, let me stick to the syllabus though. I don't want to go too much into hysteresis. If you're interested, like, I will, however, say, typically rubbers are made of like longer chain molecules which are sort of tangled together, right? Imagine a rubber band, it's kind of made of these long molecules which are sort of all tangled. What you do is when you first stretch the rubber, you have to break intermolecular bonds between all those tangled molecules. So there are these sort of intermolecular bonds in between the chains of the molecules which you have to break. So that actually requires quite a lot of force. But once you've broken those bonds to start to untangle them, what happens is they straighten out. So you've kind of untangled these long chain molecules. And then what you do is the next phase is sort of stretching or extending the molecules when they're in, fairly well aligned. And then of course it gets harder once you stretch them a certain amount and they're like this. It's going to become more difficult to stretch them again. So that's why the line starts off steep in the yellow bit, because you're breaking the intermolecular bonds initially, which have formed between the tangled branches of the molecules. Then this bit, it's slightly less steep because you've untangled the molecules and you're just stretching them, having broken those intermolecular or a significant number of the intermolecular forces. And then it gets harder again up here, steeper, when you're reaching you've stretched the material and the molecules are starting to reach them, starting to straighten out completely. So this curve behavior here is to do with this sort of structure of a rubber or resin or plastic, where you've got long chain hydrocarbons which have the potential to sort of tangle like that. Enough on that. So we've talked about force and extension. Another useful two quantities, in fact, I'd like to define are stress on the one hand and strain. And usually you'll see them given the symbol, or often you will, sigma for stress and epsilon for strain, although again, I don't think that's mentioned specifically in the syllabus. Let me check the formula booklet. No, they don't use them. So we're talking tensile stress and tensile strain. So the definitions of these are: stress is force divided by area. So cross-sectional area of your sample, F over A. And that actually tells you that its unit, if F is in newtons and area is in meters squared, that tells us that the unit of stress is the Newton per meter squared, or what's called the Pascal, which is what we give, the name we give to the unit Newton per meter squared. The strain is the extension over the original length. Which is delta L, the extension over L. So the unit of strain is actually, well, it doesn't have a unit. It's dimensionless because we've got a length in meters over another length in meters. So it doesn't have a unit. So no unit. It's a ratio. Now, I find it useful when I'm thinking about the behavior of materials or looking at a stress strain graph, for instance, to really think to myself, well, stress fundamentally is to do with the force we're applying. Yes, it tells us the force per unit area being subjected upon the material, but it's basically force. It's related to force. And strain is very much related to the extension, right? It's basically how much or what fraction of the original length have we extended by. So if my extension is half the original length, that's quite a large extension, then my strain would be 0.5. If I took my blue tack, right, blue tack here, or my sample, and then extended it so it was double its original length, or so the extension was double the original length, then, or in fact, if the extension was the original length, the strain would be 1, because I've extended it by the entirety of the original length. So strain is basically extension, like what fraction of the original length have we extended by. So stress, force, strain, extension, which means that it's not surprising, is it, that a stress strain graph looks basically the same in terms of shape, right? Look at the first bit of the graph, right? Look at the blue line. We've got straight line, Hooke's law obeyed, then decreasing gradient, and we get some interesting behavior after that. For a stress strain graph, what do we get? We get a straight line, Hooke's law is obeyed. We get a proportional limit of proportionality, elastic limit, then we get plastic deformation. So that's why the graphs look so similar, because they basically are. Stress is basically force, like plus a little bit, and then strain is basically extension. Now, let me define something else, which is important and crops up an awful lot. Young's modulus. Now, this is, confusingly, this is given the symbol E, even though energy is also often given the symbol E. Sometimes you'll see, although again, the syllabus doesn't actually give it a symbol, sometimes you'll see it, I mean, I've seen it Y, but you can just call it Young's modulus if you want. That's going to equal stress over strain. strain. And if we put the equations in we've got above, that's going to be F over A for stress divided by delta L over L for strain. So the Young's modulus, and in fact, what I'm going to do, I'm just going to check the symbol for Young's modulus. Yeah, it is capital E. There's no way around that. So get rid of Y. So the Young's modulus E is F times L over delta L times A. So this is a useful, this isn't actually in the formula book, how I've written it here. What they do is they give you Young's modulus is stress over strain, and then you could work this out, right? F over A divided by delta L over L, and put it all together. But often, if you can be familiar with this equation, that's probably not a terrible thing. But again, you can just work it out, because this crops up so much in multiple choice questions where you've got two different materials or the same material. The Young's modulus is a property of a substance. So copper, whether you have a sheet of it, a block of it, a wire of it, the Young's modulus will always be the same. It'll always have the same value. And that's useful, because if you have two samples of copper and you know the Young's modulus is the same, if they then have different areas or different lengths, you can use the fact E, the Young's modulus is the same, to work out other things. For instance, you might have to work out the difference between the different forces acting on the two. So that's Young's modulus. Notice for a stress strain graph, and I'm going to redraw a sketch down here. If you've got a stress strain graph, the gradient of the line when we're in the Hooke's law region is going to be the Young's modulus, because the gradient is stress divided by strain. That's the first thing that's worth being aware of, Young's modulus. Further, the area underneath, so I'll do the area underneath in blue, right? So say we want the area is going to equal, basically, if you think about this is going to be the stress, the maximum, well, let's just call it stress, and let's just call this strain. In fact, let me just write, there'll be some maximum stress, some maximum strain value here. And what we're doing is finding the area, which is going to be half times this value. Let's call it, well, let's just call it, for the purposes of this explanation, just treat these values, stress and strain, as the values that are on the axes here and here. I'll tell you, you'll see why. Because then we've got half times F divided by A times delta L divided by L. Now, if we rewrite that F delta L over A times L, let me show you something. Half F times delta L, we already know, is the energy stored here. Half F delta L. So this is energy stored, half F delta L. And A times L, if you think about it, if we know the cross-sectional area of the sample or the wire, and then we know its length, cross-sectional area times L is going to be volume, the volume of the sample. So you might have come across exam questions where you're asked to find the energy stored per unit volume in a sample. And this is how you do it. You find the area underneath the stress strain graph. So let me write that in full. So the area under the stress strain graph is the energy stored per unit volume. Which is, so the unit is actually, if you think about energy stored is joules, volume is meters cubed. So the energy stored would have a unit, joules per meter cubed. I'm just going back to the syllabus. Okay, good. I highly recommend, by the way, you learn this equation, you just off the top of your head, this one. Young's modulus is F times L over delta L times A, or in the syllabus it's written the other way around, A times delta L, right? It doesn't really matter, but that's highly useful. Interestingly, and this is just something to notice, if the area underneath has a unit, or I've shown that it has a unit of joules per meter cubed. Interestingly, that also shows you that the unit of stress, because stress has a unit of pascals and strain has no unit, that also means that a pascal is the same or equivalent to a joule per meter cubed. So you can go away and think about that one, that the unit of pressure ultimately is has the same dimensions as energy per unit volume. Anyway, don't worry too much about that. That's just an observation which might raise some questions. So that actually summarizes the relationships and ideas that you need in the materials topic. That's not to say that you shouldn't now go away, have a look at some multiple choice questions, have a look at some of the long answer questions, and try to put some of this into practice.